Okay, I want to give you this special video to help you prepare for quiz number 5 tomorrow. I'm going to try to make this as quick as possible so you don't have to watch for too long. First thing I want to do is I want to review some of the recent reactions that we've run. I think it's a good idea to look at these all in one place. So if I started with, for example, this alkene, which is a 1-methylcyclohexene, there are a whole host of reactions which we've learned either a while ago or recently, which are kind of related to one another. For example, I could do a standard acid catalyzed Markovnikov hydration reaction using H3O plus H2O, but I could also achieve the exact same result using this new reaction we just learned, which is a oxymercuration in the first step, followed by a reduction in the second step, and it results in the exact same Markovnikov hydration product. So for many cases there won't be any difference between those two reactions, but we'll see a case in a few minutes where there will be. The main difference is that when we use the oxymercuration reduction sequence, there's no possibility for a carbocation rearrangement because there's no carbocations involved. So I'll show you an example of that in just a moment. What else have we learned? We've learned that if we halogenate using halogen, where halogen here is either chlorine or bromine, and we do that in just a traditional organic solvent like methylene chloride, then we produce a vicinal anti-dihalide. And in this case, since that's a chiral compound I drew, this would have to be produced as a racemic mixture. Well, if we run more or less the same procedure, but this time we use X2 in the presence of either water or alcohol, then we'll produce either the halohydrin, if we do it in water, or the haloether, if we do it in alcohol. And we can show both of these reactions together. We'll still get an anti-arrangement of the two groups that add on, but we're going to see either the OH or the OR group add to the more substituted carbon. So this is OH or OR depending upon whether we're using water or alcohol. Notice that it's added to the more substituted carbon, and still in an anti-fashion, in the vicinal spot, the adjacent spot, we'll add the X. So this is halohydrin or haloether formation, and once again this would have to be produced as a racemic mixture. We've also learned that we can simply hydrogenate very easily alkenes as long as we have a transition metal catalyst like a platinum or a palladium. And that's just going to give rise to the alkane. We're going to add hydrogen across that pi bond in a syn fashion, as it turns out, but it won't change or introduce any stereochemistry here, so just draw it like that. What else did we learn? We learned recently that if you treat these alkenes with peracids like MCPBA, then you can produce the corresponding oxirane or epoxide. Those words mean the same thing. And of course, since it's a three-membered ring, it must form in a syn fashion, meaning that the oxygen's either on the front face or the back face. Since that's a chiral compound, we must produce a racemic mixture, which just simply means we're just as likely to put it on the front face as we are the back face. And lastly, a reaction we learned recently, which is somewhat related to these first two, these hydration reactions, is an anti-Markovnikov hydration, a two-step sequence, hydroboration oxidation, which produces an anti-Markovnikov hydration product. So we're going to make an alcohol, and it also occurs in a syn fashion, and we can pick up all of that information if starting with this particular cycloalkene that we've got. So for example, anti-Markovnikov means that it is the hydrogen that adds to the more substituted carbon, and the alcohol that adds to the less substituted carbon, and they add in this nice syn fashion. Over here, where we had halogenation, they added in an anti fashion, and that's also true for halohydrin or haloether formation. That's also an anti-addition over there. So those are some recent reactions that we've learned. I think we could actually take a peek at a couple more. What if I start with a 1,2-dimethyl cyclohexene, and now I hydrogenate? Now, not only will I see in the product that I've added hydrogen across that pi bond, but I'm also going to see that it adds predominantly in a syn fashion, which means both of those methyl groups would either be pointing to the back or to the front. You don't have to draw the hydrogens in, but if you drew them in this case, they would both be pointing to the same side, in this case to the front. So it is a syn addition of hydrogen across that pi bond. And then where alkynes are concerned, we learned actually 3 different hydrogenation approaches. The first is just to run a standard hydrogenation using hydrogen and palladium, and in this case you're going to hydrogenate both pi bonds and go all the way to the alkane. You can slow that second hydrogenation down, in fact stop it, by using Lindlar's catalyst. That's a poisoned catalyst, and that will stop after 1 syn hydrogenation. You can see it is syn because it produces the cis alkene. And finally, if you use a dissolving metal reduction, which is sodium in liquid ammonia, then you can have the anti-addition of hydrogen, anti, to give you the trans alkene. So that's probably the vast majority of the new reactions we've learned. It may not be all of them, but those are the ones that come to my mind right now. Let's look at some synthesis problems. And in these synthesis problems that I'm about to give you, I am going to try to emphasize some of these new reactions. But I'll also bring up some old reactions, and I think that's important, because in organic chemistry, we can't forget any of the old reactions we've learned. We're going to have to use them in synthesis problems just like this from this point forward. So here's a synthesis problem number 1. Let's convert this bromide into this alkane. It is a 1-bromobutane, and we're going to convert it into butane. The number of carbons is exactly the same. How do we do this? Well, you've known how to do this for quite a while, because we could, for example, make an organometallic, which could be a Grignard reagent or an organolithium. I'm going to show the Grignard reagent here, using magnesium zero in ether. And then if we just treated that with H2O, that would complete the synthesis, because we know those organometallics are very sensitive to water. They're basic, and they'll pick up the acidic proton off of water very, very easily. But actually, now we know another way to do this. So for example, using an E2 elimination with our E2 base of choice, potassium T-butoxide, we would produce the 1-butene alkene, taking advantage of the alpha hydrogens which are present at this carbon right here. And then we could just hydrogenate that using hydrogen and palladium. So we know 2 different ways to synthesize that molecule, so that's quite useful. Let's look at another synthesis problem. Actually, this is going to be 2 problems. So what I want to do is I want to convert this alkyne into an epoxide or an oxirane. And in one case, I want a cis stereochemistry. The two ethyl groups here are cis with respect to one another. And in the other case, I want to have a trans stereochemistry. The two ethyl groups are trans with respect to one another. So how do I go about doing these two syntheses? Well, I hope you remember that in order to make an oxirane, that's one of the reactions we just talked about, we're going to need an alkene. And if we have an alkene, we can treat it with a per acid and we can make the oxirane. But in order to get this particular oxirane right here with the cis ethyl groups, I'm going to have a cis alkene. So this cis alkene right here can be converted through an MCPBA reaction to the corresponding oxirane in which the stereochemistry of the alkene is maintained. If you start out with a cis alkene and you have a concertative reaction, which this oxidation with a per acid is, completely concerted, then these are going to have to remain cis at the end of the day. And I can convert my alkyne into this cis alkene using H2 and Lindlar's catalyst. So there's my synthesis. Step 1, H2 Lindlar's catalyst gives me the cis alkene. Step 2, MCPBA or other per acid gives me the oxirane in which I maintain the cis stereochemistry. Conversely, if I treat my alkyne with sodium and liquid ammonia, then what I'm going to do is I'm going to produce the trans alkene, which in turn can be treated with MCPBA in order to produce the trans epoxide or trans oxirane. Again, maintaining the stereochemistry of that alkene because the MCPBA reaction is concerted. So there I've laid out my two syntheses. Let's try a different one. Here I'm going to start with an alkyne again. I'm going to produce a vicinal dibromide, and notice that I'm not indicating the stereochemistry. That makes it actually an easier problem. You don't have to worry about stereochemistry. You just got to get a couple of bromines at those positions. So how would we do this? Well, I hope you remember that a precursor to a vicinal dibromide would be the corresponding alkene. And in this case, since I'm not indicating any stereochemistry, it could either be the trans alkene or the cis alkene. Either of those approaches would work. The way we would take either of those two alkenes and convert it into the vicinal dibromide would be to use bromine in the presence of a nonpolar organic solvent, something like methylene chloride. And as we've already seen, we can convert the alkyne into either the trans alkene using sodium and liquid ammonia, or the cis alkene using H2 and Lindlar's catalyst. Now in a case like this, and maybe even in some of the other cases I've already shown you in this video, when you give your final answer on a quiz or on an exam, you want to clean it up a little bit. We've got a couple different pathways here, so we're not really indicating a single answer, which we always want to do. So what I would do in a case like this, if I had this these notes on my paper, I would go down to the bottom and I would say something like answer, and I'm going to start with that alkyne, and I'm just going to choose one of these approaches. So let's just say H2 in the presence of Lindlar's catalyst. It's going to give me the cis alkene, which then I will brominate in an organic solvent like methylene chloride to give me the corresponding vicinal dibromide. So that's a nice clean answer, and that's the way you should try to end your synthesis problems, with a nice clean answer like that. Alright, let's look at another one. here's a new synthesis problem. Now, what you want to do in a case like this is look at this product, examine it for a moment, and see if you see any clues as to what reaction would have led to it. Hopefully what you see is that there's an alcohol there, so we know a couple of different reactions which produce alcohols, including hydration reactions, where we add H and OH across a pi bond. Is it possible that this came from a hydration reaction? Well, if it did, notice that the alcohol is at the less substituted carbon. There's a more substituted carbon right next door. And that sort of screams to us that this could very well have been an anti-Markovnikov process. So if I started with this alkene and I had treated it with borane in the first step, that's the hydroboration, followed by an oxidation with hydrogen peroxide and aqueous basic solution, then I would in fact produce this very same alcohol, because the result would be a syn hydration. Notice that it is syn, even though the methyl group was in the back. What's added during the course of the reaction is the OH and the H, and they must have added in a syn fashion. So this is my retrosynthetic analysis. It seems reasonable that an immediate precursor to this final structure would have been this alkene. And the question is, can I get from this chloride to that alkene? Well, I could, for example, try to perform an E2 elimination using my potassium T-butoxide, my E2 base of choice. And that would necessarily give me that structure. Could I get that alkene converted into that alkene? I think so. If I treat this, for example, with HI, this would be a Markovnikov hydrohalogenation, hydrogen to the less substituted, halide to the more, followed by yet another E2 elimination. I would produce the Zaitsev product, which is the more highly substituted alkene. So I've got it all here laid out pretty cleanly, but I still would probably, if this were me answering the problem, I would go down here and write, well, let me write down my final answer in a nice clean way. So I'm going to start off with my starting material. I'm going to run an E2 elimination. I'm then going to treat that with HI to give me the Markovnikov hydrohalogenation product, which I am then going to perform another E2 elimination on, this time to give me the Zaitsev product. And finally, I'm going to perform an anti-Markovnikov hydration to give me my final product. All right, I've got one more synthesis to share with you, and here it is. Let's try this one. So we're starting off with a chloride, and we're going to make a tosylate. Let's make sure all the number of carbon atoms remains the same. 1, 2, 3, 4, 5 carbon atoms, and 1, 2, 3, 4, 5 carbon atoms, so that's all good. There's no funny business in terms of adding or replacing carbons, or removing carbons, I should say. As we get a little further on in organic chemistry, we're going to see that there are reactions that do both of those things, some that add carbon atoms and others that reduce the number of carbon atoms we've got. So it's a good idea, even at this stage, to get in the habit of counting up the carbons on both sides and making sure that that's all the same. And if it's not, then planning out the synthesis accordingly. Well, this tosylate, I hope you recognize, must have come from this alcohol. There's just no other way to make the tosylate. So we start with the alcohol, we treat it with tosyl chloride. So that had to be an alcohol right there. Now this is closely related to the starting structure. I've got a chloride, but this is an alcohol, and it looks to me like this alcohol could have come from an alkene if it were, for example, a hydration process. And the alkene would have had to have been right there, which means right here, starting with the chloride. So probably a reasonable thing to do would be to treat this with potassium T-butoxide for an E2 elimination. which would give me that alkene. Now what I want to do is I want to convert that alkene to that alcohol. This is a step, however, that we have to think about very carefully. Let me go down here and show you what would happen if you just treated this with standard acid catalyzed Markovnikov hydration conditions. I do want to have a Markovnikov hydration after all. I want my hydrogen to go to the less substituted carbon and my OH to the more, hydrogen to the less substituted carbon, and OH to the more gives me this structure. So I want to have that, but if I just try to run a standard Markovnikov hydration, I'm going to produce this secondary carbocation, which will undergo a very rapid Wagner-Meerwein rearrangement because there's a hydride right next door. Which can move to the secondary carbon, taking the 2 electrons with it, giving me a tertiary carbocation. And then when the water adds in, although it may add in to a small extent at the secondary site to give me ultimately the desired product, the majority of it will in fact add to the rearranged tertiary carbocation. So this has got everything to do with carbocation rearrangements, which we've discussed. There are certain molecules, in particular those that produce secondary carbocations that can rapidly and effectively rearrange tertiary carbocations through simple hydride or methide shifts, the Wagner-Meerwein rearrangements. Those are the ones that we've got to really be worried about. In my synthesis, going back to my synthesis now, I want to go from this chloride to this alkene to this alcohol to this tosylate. I cannot have this rearrangement take place, otherwise it's going to really wreak havoc on my synthesis. So I need to hydrate this in a Markovnikov fashion without a carbocation rearrangement, and that is exactly what our oxymercuration reduction sequence does for us. It hydrates the alkene in a Markovnikov fashion without the possibility for a rearrangement. So that is going to be my final answer. I'm not going to spell it out for you like I did on the other problems, but step number 1, E2 elimination to form the alkene. Step number 2, Markovnikov hydration without rearrangement. And step number 3, formation of the tosylate using tosyl chloride. I hope going over these synthesis problems was helpful to you, and I'll see you tomorrow.